Good afternoon. I'm Hugh Dyer, Associate Director in RSK's Geoscience business. Welcome to the first of our 2024 series of Down to Earth webinars. These will cover a broad range of subjects through the year and are available afterwards on our YouTube channel alongside previous talks. Our talk today will be given by Dr. Charlotte Usher from our geophysics team, giving an engineer's guide to the use of geophysics within site assessment. Firstly, a brief note on housekeeping during the talk. All attendees' microphones are automatically muted through the webinar. During the presentation, you can post questions. Please post questions online, and there'll be a Q&A session at the end of the presentation. We aim to answer as many questions as we can afterwards. Those that can't be answered due to time constraints will be answered after the webinar. Shortly after the webinar, you'll receive a link to a short survey. If you could take a few minutes to provide feedback, please do so we can improve future webinars. So now to our talk today. Please let me introduce our speaker today, Dr. Charlotte Usher. Charlotte is a chartered geologist and a principal geophysicist. She joined RSK following her PhD and has now been part of our team for nearly 9 years. Charlotte is technical lead for geophysics within RSK and is actively involved in research and development, as well as working on large-scale commercial projects. Recently, Charlotte has been the lead author for the new Syria guidance, C812, that was published mid-December last year. She was also a finalist for the Rising Star Technical Excellence category for the Inspiring Women in Construction and Engineering Awards. She is looking to make the communication of geophysics more accessible to increase engagement and use in ground investigations. So I'll hand over to Charlotte now to give us an engineer's guide to the use of geophysics.
Brilliant, thanks Hugh. So as Hugh mentioned, around 2 years of my life, between 2022 and 23, I've gone into writing the Syria document C812. The act of writing this guide and discussions we had during project steering group meetings, they've been a really big inspiration for this talk. It's through that process, it made it very clear to me, as it had to those who decided to update the previous Syria document. The way that we talk about geophysics needs to change so that we can help convince more people it's worth giving it a go. If I can give one more person here today a feeling of confidence about using geophysics during that project, then that's great. So today I'm going to be discussing, as you mentioned, specifically the use of geophysics as a ground investigation tool. That's my background. That's what I do day in, day out. Most of what I'm discussing will also be relevant for use of geophysics in things like non-destructive testing as well. And this talk's aimed at people who are looking to commission geophysics surveys, not so much for the practitioners of geophysics. And much like the Syria guidance, I'm trying to emphasize what would be considered a good practice within geophysics surveys. To do this, I've got these 5 main topics I'm going to discuss today. So first, I'm going to discuss what is geophysics, trying to put that into layman's terms. Second, I'm going to be discussing the most effective way to use geophysics within a ground investigation. And then that second section will then feed nicely into section 3, which then looks at the potential cost benefits of geophysics. That's then followed by looking at the role of everybody, including the geophysicist, within a project, what they need to provide and how you can tell if your geophysicist is competent in what they're doing. And I'm then going to finish that with a summary guide of what you, as a client, for example, should expect to receive at each stage of a geophysics investigation. So, moving into the dark arts that are geophysics. Geophysics. So, it's considered a range of tools that are they're integral to creating a representative ground investigation. They provide information on the properties of the different materials, and they identify changes within the subsurface. It works by applying the principles of physics to the study of the Earth's materials. So this includes electrical, magnetic, gravitational, seismic, and other techniques that are all used to investigate changes in the relevant properties and then the structure of ground materials, showing how they change within the ground based on the changes in these properties. The best interpretation of a ground model will come where we have a good understanding of the physical ground structure. So this usually comes from using intrusive investigations alongside the geophysical data. The most robust ground model will use geophysics to provide a greater data coverage of the site, which means you can then understand better the continuity of any geological, geotechnical, hydrogeological information that are in between intrusive sample points. Geophysics can provide an overall cost benefit to the ground investigation, but only where it's used effectively, which I'm going to discuss shortly. It reduces the risk on site from both known as well as unforeseen ground conditions. And most importantly, I feel, when there is collaboration between the engineer and the geophysicist, this needs to happen for any practical evaluation of the results. Lots of geophysics data is good. I'm obviously a big advocate of geophysics data, but the ground model that's produced from geophysical data cannot be adequately constrained without any direct information of the site-specific ground properties. It's just going to be a best guess without those. So now you know what I'm talking about. The next question is, when is the best time to use it? A big thing I'm going to be emphasizing within this presentation is that taking shortcuts wherever within your ground investigation does not generally produce a cost-effective or efficient investigation. While there are not many specific standards, British standards, on the different geophysical methods, there are some recognized standard approaches within geophysical investigations. There are also international standards, such as the ASTM standards, that do refer more specifically to different techniques. But obviously, with regulations in different countries differing, there may be some variation. Obviously, as I've already mentioned, Syria C812 is the latest guidance, which is along a similar theme as the book Engineering Geophysics, which is by Medhurst and Kinkby, which looks at geophysics from the perspective of those looking to commission the geophysics survey rather than the practitioners. It is intended as an update on Syria C562, although a lot of the science within that document is still relevant. So when we're thinking about where geophysics might fit in within a ground investigation, we also need to consider how it's going to be used, and this should be thought about for every single investigation that you do, basically. Geophysics surveys can be planned and carried out prior to intrusives to then help inform on the design of any intrusive investigation. And this is a practice that's already well established in archaeological surveys. SUMO services actually state that the use of geophysics can reduce the amount of trenching sometimes by over 50%, which is obviously quite significant. Intrusive investigations can then obviously be used to target any anomalies found within the geophysics data, either to identify their cause or to calibrate or validate your geophysical interpretation, or even just to avoid any risks, particularly when the geophysical investigation is being used for looking for unexploded ordnance, for example. An important element of this is the client or the engineer then obviously needs to collaborate early on with the geophysical specialists, and between them, they can then determine if a geophysical survey will even work for the site in question. And then this can then be designed, the geophysical investigation can be designed and then effectively programmed within the scheduling for the ground investigation. Ultimately, it is best to consider using geophysics at each stage of a ground investigation, but in particular, consider it early on in your design. It's really important to emphasize that the choice of the geophysical technique, or even whether or not to even use it at all, will be site specific. Just because something worked on one site doesn't mean it will necessarily work on the next. So we have this diagram, for example, shows the sort of questions it's generally worth asking before deciding if it's worth using geophysics in your ground investigation. And as always, if you're not sure, you can always ask for free advice from your friendly geophysical specialist. Now, moving on to the cost benefits. Now, obviously, this is probably a fairly major factor of why people have potentially come on this talk. And a big issue that people have with geophysical surveys is generally that they are not considered cheap. People see the cost, they don't want to pay it, and that's that. Done, I'm not using it. But the key thing really is to look at this geophysical survey as part of a bigger picture. The other issue is the cost of a geophysical survey is really difficult to quantify, which is what I'm going to go into now. So there's lots of different things that can affect the survey rates of your geophysical survey. So things like mobilization costs. How far does your geophysicist have to travel to get to site? What type of survey are you using? How many people are needed to do this technique? Do you need to hire any equipment? What detail do you need that survey to be completed to? How big is the survey area? How complex is your local geology or the target you're looking for? Is the access to your site limited in time, or is it difficult to access? Are there any additional health and safety requirements? Do you need welfare on site, for example? Do people need additional time to process the data or interpret it or present it? So do you need 3D CAD plans? And finally, are there any additional overheads? So do you need to pay for accommodation where people are working away from home? Are there third-party costs such as traffic management? These are all things that then add up. Then, on top of that, you have to consider the scale of your survey. A simple single-day survey can be under £1,000, whereas a fully comprehensive multi-technique phased survey can be over hundreds of thousands of pounds. And there will be potentially some variation between different organisations, but as with any survey, the more time you spend on site, the more effort that is invested by your specialist will generally mean a greater cost to the client. As I mentioned before, big picture, it's a big takeaway from this point. When geophysics is used effectively, so this is considering it early in the planning stages of a project, the additional cost of using it can usually be offset by a reduction, for example, in the number of boreholes that then need drilling. A major cause of increased cost within ground investigations is when a survey overruns, so it takes longer than you anticipated. A big cause, like the main causes of overruns, cost overruns within a ground investigation, generally occur during the planning and the interpretation stages. So when risks and hazards on site are improperly identified or where data has been misinterpreted. If people react to a geophysics investigation by just seeing it as expensive or unnecessary, this can sometimes result in sites that are then forced to use geophysics reactively alongside an untargeted intrusive investigation because they've encountered some unforeseen hazard or ground condition. These can then slow or halt the process of the GI completely. Sometimes this can be things like a service strike, which can obviously result in fines as well as being a massive health and safety risk, which none of us want. And as most of you already know, careful survey design will be key to maximizing any cost benefit you get from a survey. As we know, there's always a set of fixed costs with any survey, such as getting to site before you've even collected the data. While I am a strong advocate for trying to get the most information from a survey, more data is good, there are certain instances where additional data might be redundant to any survey outcomes, such as re-repeating a data line when data has already been shown to be good and robust. However, attempting to cut costs on a geophysics survey, such as use of on-site markup over post-processing, or using one technique, ignoring the specialist's advice to use multiple techniques, can be detrimental to a project. And that's demonstrated in the defined accuracies in the PAS 128 standards. These are a set of benefits and limitations on the use of geophysical surveys. I'm not going to go through these in detail, but I'm just going to summarize a few points. You might notice that some of these seem to contradict each other somewhat. It's important to remember again that these are going to be site and technique specific. The choice of geophysics technique has a big weight on the success and the cost effectiveness of a survey. And obviously, if it's been poorly conducted or people have used the wrong technique, it's generally going to be a waste of money. Overall, geophysics surveys tend to have little to no interference with what's already on site, and in many cases you can't tell we've actually been on site a few days later. And due to the fact that some techniques don't even break the ground surface, these are considered safer to use on site where we don't want to affect the integrity or the stability of the material, such as listed buildings, or where there's potential hazards on site, so UXOs, asbestos, contamination, or voids. And obviously, a big benefit of this is you get extra information. This can then be integrated into your ground model and help make the conclusions you have about what's going on underground more robust. So I'm now going to talk about the roles and qualifications. So first, we have the client. What do they want? What do they need? Generally, their requirements can be boiled down into three main elements. They want information from the ground investigation that's correct and accurate at the time of issue of that information. They want good communication from their engineers. This will then help prevent issues arising from the site, particularly those for which the client has no warning of. And they want a cost-effective survey, which doesn't necessarily mean the cheapest, but it does mean the best value. It's also the client's responsibility to ensure that all parties understand what they're doing in a project. Sometimes a client will bring on an advisor for the geotechnical or environmental aspects of a project. And much like the geophysicist, they need to be competent and experienced to then be able to take on the responsibility for all aspects of that ground investigation. If needed, the client can also seek advice from a separate geophysical specialist, either from their own organisation or an external company. And if they choose to appoint a geophysicist, sometimes they can do it directly themselves or through a contractor. The level of involvement of your geophysical specialist within that ground investigation will depend to a degree on who they're working for. They are, however, often one of a few contractors whose data gets reported directly to a client or principal contractor or designer of a survey, even if it's part of a larger body of work. The client needs to ensure that the geophysicist has access to all the information that they need, such as the objectives of the ground investigation, what the geophysical survey needs to achieve, and if there's any additional site-specific restrictions that they need to be aware of, such as limited hours. All parties need to work with the geophysical specialist. Successful projects are usually completed where all parties work as a team to meet the objectives, which can help incentivize savings between all parties and drive innovation. Applying the right method first time and then delivering the correct information will generally give the best value for a project compared to having to pay out twice because the cheap option obviously didn't deliver. And working together can then also help to best fit those geophysics surveys within the acquisition program and then tie those results in to the final model. Where possible, it's generally useful to try and provide the geophysicist with additional site data, which can then aid in their interpretation. But if geophysics is being used as a reconnaissance survey, that might not be available immediately. Again, I'll discuss that a bit more later. When we were writing up the CIRIA guidance, the qualifications of a geophysics was another topic that was a big discussion. It's not officially defined anywhere specifically as to how a geophysicist should be qualified. The CDM regulations of 2015 say that all staff on site must have the appropriate skills, knowledge, and experience in the techniques being used. So this will be true for your geophysicist as well. When a geophysicist is inexperienced, they might not be able to adequately quality check during acquisition, or are more likely to misinterpret data, leading to misleading results. Qualifications such as degrees will generally provide the core engineering and scientific understanding, and most specialists will have degrees in relevant areas that will relevant areas to geophysics. It's also a reasonable expectation for geophysicists to have a postgraduate qualification and hopefully experience in relevant methods to be used. Senior staff who sign off and therefore take responsibility for data and outputs of a survey on behalf of their organisation should be professionally recognised, such as being chartered through a relevant organisation, and importantly have a number of years of relevant experience, usually a minimum of 4 to 5. Graduate geophysicists, in comparison, will typically have the degree experience but no practical experience of survey execution, except the most basic and repetitive parts of a survey. There's not any current educational or industry standard for a field technician or assistant, and generally they will learn directly from the guidance and supervision of the senior geophysicist. Regardless of who has appointed the geophysicist, the output of the survey will be the same. If people looking to commission a geophysical survey have no geophysical knowledge themselves, they should probably consider consulting a geophysical technical advisor. It doesn't matter if that advisor is internal or from an external specialist consultancy, and it might be the geophysicists that end up doing the work or somebody completely independent. But that technical advisor needs to understand what the client requires, why they need it, the accuracy or confidence they need to know that information by. They need to determine if geophysics is even suitable to use on site and be honest about how likely it is to work, advising that client on both the benefits and the limitations. And if needed, they can also help to design and acquire the data, but generally they'll act as a point of contact for any geophysics information for the client. So, finally, do you know what you're meant to be getting from your geophysics survey? Are you getting what you paid for, and how can you tell? So I'm going to go through the different elements of the survey to define what you should expect to get at each stage. So first we have survey design. Sometimes this will have been defined in detail by a larger scope. This is quite common when a client has sought advice at the early stages from a geophysical specialist. In other cases, the client just goes straight to the geophysicist, says, here's my survey area, here's my target, and in these cases, the survey is designed by the geophysical specialist. Any quotations should include things like mobilization of staff, hired equipment, on-site staff hours, management time, data processing and reporting where it's appropriate, any relevant training that's required, such as working at height or if there's any additional PPE. It also needs to include things like the time spent on acquisition and processing. Again, this will vary depending on the complexity of the site or the technique. And lots of consultancies tend to offer all these elements within one organisation. Sometimes surveys have to be priced per distance. Sometimes they include day rates if surveys are disrupted or delayed. But obviously, an overall cost for a survey and the best survey design will come where there is sufficient information from the client of the survey requirements. There's several elements that a geophysicist will be considering when designing a survey that can affect the feasibility. So is it even going to work? So for example, if you're considering the materials you want to look at, is there enough difference between two materials for it to be detected? For example, if you're looking for a fault between two different sandstone units, unless there's weathering or fluid within a fault boundary, you're not really likely to see it. And this is something a geophysical specialist will advise on. If there is any doubt in the feasibility of geophysics or its ability to return information with a desired accuracy, then a trial survey could be suggested. This is generally used to survey a smaller area to test methods and evaluate what approach should be used for a larger scale investigation. A reconnaissance survey is slightly different. It's typically used as part of a phased survey approach. Geophysical mapping techniques are generally used to map a large area, identify features that can be then targeted with more detailed surveys, either further geophysical surveys or an intrusive investigation. Each of these different things can then be used to refine the main survey design or even to proceed without any further geophysical investigation. Data acquisition should always include someone on site who is competent and experienced in what they are doing, and hopefully in the environment that they're doing it in. Acquisition also needs to include accurate positioning of all survey elements, important features on site, and clear and concise field notes, which should be made available to the client on request, which will include things like the weather and ground conditions that are relevant to processing. When it's feasible, the geophysicist could do some initial interpretations of the data that should be regularly reviewed. And then this can be used to modify the survey plan, adapting to ensure the data is acquired in the most efficient way possible. So once the geophysicist has acquired their data, the data needs to be processed from a file of seemingly random numbers into something more useful. It's important that the person processing the geophysical data is competent and has experience in the processing steps and software for the relevant technique. This includes understanding what is a dodgy data point or what is anomalous, what is obviously different from what should be there. They need to understand how to apply the different algorithms that are used to enhance the signal from any background noise. Processing of the data, depending on the equipment, can take several days, even if it's just from a single day in the field. So, on to the data interpretation. This is arguably where we get the most subjective bias, so different people will see patterns differently. It's yet again important to note, I am re-emphasising this point, the geophysicist undertaking the interpretation needs to be competent and experienced in the interpretation of the relevant data. There is no point in having a seismologist try and interpret EM data. The geophysicist needs to be able to use any prior knowledge from the site to aid in their interpretation where it is available. So this will be any on-site observations, any intrusive information that can be provided by other site operatives should also be used. And this can be used iteratively after the fact. So data can be interpreted once. This is used to target your intrusive investigations, which provide further information, and then the geophysics data can be reinterpreted. Data interpretation can change quite a bit when there's more information to use that will help limit factors such as the number of layers of a material type, which can then obviously impact your final ground model. It's quite a cyclical thing, but you can see why teamwork is really important. And most importantly, the need to ensure that the interpretation of the data provides the information the client requires or indicates why it can't answer those questions. It's really important as well to clarify where and how large any uncertainties are in a way that's clear to everyone involved in the project. Finally, the report. In some cases, the client will request a factual report, and in this case, the geophysicist will provide the results only with data ranges, quality. It may include a presentation of the results, but with no geological interpretation of the data. An interpretative report means data processed and presented as a model of a measured ground structure. This can also be referred to as an inversion. It's interpreted referencing the expected geological model or target, and highlights any features of interest. A number of things that are described in the report are generally there to help fully describe the survey, how it's been undertaken, how it's been processed, how it's been interpreted, and the level of detail they need to include in that would then mean that a survey could be repeated again if necessary. Any subsequent investigation on a site can then be used to refine the ground model that's then derived from the geophysical investigation. And it's important within the report to clarify any limitations that the geophysical survey had, with a real importance to emphasize that the failure of a geophysical investigation to detect a feature on site does not mean that it does not exist. So, in summary, in geophysics, we have a wide range of tools which are used to develop a more robust ground model. It's really important for all roles within a site investigation to collaborate, to work as a team, to make a survey efficient and cost beneficial to all parties. All workers, including the geophysicists, should be competent and experienced in the appropriate survey techniques and in the environment they're working in. The most cost-effective surveys are generally designed where the most information about a site has been supplied from the client to the geophysical specialist. The failure of a geophysical investigation to detect a feature does not mean it's not there, and every site and technique will have its limitations. But overall, just because it didn't work last time doesn't mean it won't work this time. And if you're not sure, ask. References for anybody who's interested. Thank you for listening.
Thank you, Charlotte, for that excellent talk. I've learned a few things in there, and we've had a few questions come through now in the portal. So first question, firstly, is it important to have a basic knowledge of geophysics before approaching a geophysics company to get the scope and costs?
So I don't think it's important for people to have specific geophysics knowledge. We have, for example, our own fact sheets that we would commonly provide clients, particularly for techniques that we're going to use, which are taken from our geophysical handbook. I mean, if it were me, I'd want to know a little bit of what to expect, to know if the person that I was talking to was trying to pull a fast one, and if they were actually worth spending money on. I mean, the last thing people want is to spend money on a survey, whether that survey was the cheapest or not, and then find out it has to be redone because those results are useless and the person had no idea what they were doing. You can solve that to a degree by going to multiple geophysical specialists, getting quotes from a bunch of them, seeing how well they line up, and usually you'll get an idea of how sensible a specific quote sounds relative to how well these quotes line up.
Brilliant, thank you. What information is needed to be provided to allow design of a geophysical survey? So generally we need to know a good red line boundary, a good outside of where the limits are of where you want to survey, what specifically your target is, if you know any details about that target, so what it's made up of, any orientation of that, burial depth, all that sort of information, that's also great. What detail of information you need that to, because obviously if you need really fine detail at depth, then that's going to be a lot more difficult for us to provide than it is otherwise. Yeah, so as much information as possible, basically. Hopefully that answers the question. Excellent. But obviously you can do desk study and find out the site setting. So another question is, do you do modelling or do you do modelling before planning a survey? And do you only do the site investigations, or do you do geophysics in the lab as well? So we will do forward modelling
of certain survey types to see if they're feasible, such as microgravity. As a technique, that one's very expensive, both in time and financially, generally, to complete. It's used often as a second phase technique, but we will always forward model that information to see if it's even going to work for a specific target in a certain environment before we suggest it. And there's other techniques that we can do that for as well. So that's kind of the extent of modeling that we do in terms of survey design. We don't specifically do any in the lab, but obviously there have been examples of certainly in academia where geophysics has been used in lab-based situations, which we can refer to if there's been a peer-reviewed paper.
Right, okay. How are geophysical surveys impacted by reinforced concrete or surface coverings, say tarmac or concrete coverings, and the ground coverings?
Yeah, so that depends on the technique. There's a lot of techniques that are very good at finding the reinforcement. A lot of them struggle to look below it. There are workarounds in certain situations, but a lot of the time for certain techniques, basically, if you're looking for something below reinforcement, it's very difficult for us to do. But again, it's going to be site specific. It's going to be reinforcement specific, because obviously some reinforcement net meshes are finer than others. And this will all influence what we would advise within the situation.
And a follow-up from that is, if you do have reinforced concrete surface covering or similar, can you then do investigation through holes in that concrete that will give you the structure underneath?
So we can, if you're referring to geophysics down boreholes, then yes, we can do that. But obviously any information is going to be localized to those boreholes, as it would be for any technique. We do, when we're surveying things like petrol forecourts, which are reinforced, we are able to get some information through the rebar using surface techniques, by using things like a range of frequencies of ground penetrating radar, for example. But again, site specific.
Yes, yes. Yeah, of course. I've got a question here. How deep can you go with investigations? And also, can you do angled investigations, say if you can't get access to certain areas of the site?
So the depth will again depend on your technique. With radar, we tend to go with the different frequencies and state how deep they go. So the higher frequencies will go centimeters, whereas the lower frequencies will go 10, 12 meters. But with other cross-section techniques such as seismics and resistivity, you can go 50, 100 meters deep. Just make the source bigger, effectively, you can go deeper. But the issue is, as soon as you go deeper, your level of detail will decrease. So there's a trade-off between the depth and the resolution of your information. So that's generally one of our main issues that we have with geophysical surveys is, yes, we can do depth, but the detail you're going to get is going to be not as good.
Right, okay.
There was another part to that question, but I've forgotten what it was. The angled one. Yeah, so we have had a few surveys where we've not been able to access things directly. If you've got a topographical change, that's going to be the surface from which you're reflecting from, and so the actual angle of your survey is going to be relative to that surface. But unless you're drilling an angled borehole, there's not really an easy way to do an angled survey. It's difficult, basically, because the energy is just going into a surface.
I've got one here. What is the optimal spacing of geophysics boreholes or points? And how can you qualify uncertainty or zones of uncertainty?
So generally we say the spacing of points is going to be approximately equivalent to your resolution. So if you have, for example, geophones within a borehole that are spaced 1 meter apart, then that's going to be your level of detail that you're going to require. In terms of uncertainty, we tend to do things like repeat measurements to identify how repeatable results are, and obviously if they're coming up the same every time, then we have a greater certainty of that actual physical measurement. We will be able to use that to apply error bands to a value, and then that will transfer through into any inverted values as well. And every inversion from property into a ground material will in itself have a measured misfit between a modelled value versus what's been measured, to show you how good that fit is compared to what's actually been measured in the ground.
Right, excellent. Can geophysics be useful on small sites, say less than 1 hectare, and then how much area can you cover in a day in a geophysics survey?
Again, it depends on the equipment. Mapping techniques such as GPR or EM can be very rapid and cover that area easily within a day. But this will obviously depend on the level of surface obstructions that are present. So are there any parked vehicles? Are there any stockpiles? How deep is the vegetation on the site? Anything that kind of blocks our access is going to slow down any approach. With other techniques such as gravity, that's going to take a lot longer to acquire, which again is why I said we tend to use that as a more targeted approach. So you do your mapping first and then target the gravity on specific features. So it takes a lot longer to cover that sort of area with certain techniques.
Right, and is it useful on small sites as well?
It can be, but it depends on what you're looking for. I mean, if you're looking for, say, metal targets within this site, then it can be rapidly mapped and you don't need to do any digging. We can highlight any sort of like anomalies, you know, prior to anybody going out and doing any further site, and we've used that quite a lot for UXO surveys. But if that small site is a brownfield site, there's lots of metallic debris on the site, it might not be as useful. So it can be, but it depends what you're looking for and right. What your budget is.
Okay.
We used it in back gardens before, so you know that's a fairly small site.
Well, I suppose it depends whose back garden.
Yes.
That could be a large back garden.
Yeah.
What type of ground would give a lot of noise and disturbance? And are there chemical constraints such as salt, metal content, contaminants in the ground that should be considered when designing an undertaking?
So things that are going to cause noise over any signal is going to be basically the properties that are being measured by the equipment. So for magnetic surveys, it's going to be anything ferrous. So if you have rebar on the surface, if you have shards of metal, that's going to cause noise interference. If you have an electromagnetic survey being undertaken, so you've got GPR, you've got EM mapping, it's going to be metal fences, power lines, radio towers, any sort of source of electromagnetic noise that's nearby. For seismic surveys that use sound, it's going to be things like the wind, any vehicles nearby, if there's any drilling going on, anything acoustic noisy that's going to interfere with those surveys. So sometimes it's things within the ground, sometimes it's things outside the ground. What was the second part to that question? Sorry.
contaminants or salts?
Contaminants, that's it.
Things in the
Yeah,
ground?
so again, that's going to depend on the survey type, but for things like electromagnetic mapping, which we have used to map contaminants within the ground, these materials are generally going to appear with, say, a higher conductivity, as is salt water. We're not necessarily going to be able to tell the difference between salt water and contaminants with just one technique, but it might be that use of multiple techniques can be used to classify the differences between these. But in this case, you'd probably need some intrusive sampling to go alongside your geophysics survey to be able to properly classify the difference. If you're not looking to measure those, then they can in themselves be considered noise. If you're looking for a landfill boundary and you didn't know there was a contaminant plume there, for example, then potentially that boundary is going to be less clear because of that contaminant plume. So, yeah.
Right, fantastic. Right, I think we'll end the questions there, and any further questions will be answered once Charlotte has had a chance to review them and regain her composure. Our next Down to Earth talk will be on Tuesday, the 13th of February, and that'll be focusing on economic design of ground improvement. Please remember to complete the feedback following the presentation. And thank you ever so much for attending today, and we'll see you again in February. Thank you very much and good afternoon.